So now it's time for us to begin our new chapter, which is Sets. That's the second chapter in our book. So first, we're going to discuss a bit about the notation, because there will be some ways for us to write. What kind of sets are we talking about? What are the elements? How can we compare sets? Then we'll discuss a few number sets which are important, right? We're gonna name a few number sets which we'll use in our mathematical lives until the end of our lives, right? Then we'll also take a look at interval notation. That's another way of looking at numbers. We'll discuss Venn diagrams, which is the bulkier part of this unit, and also there will be some operations that we can do with sets, which is the union and the intersection. So, starting from the beginning, our set notation. Well, what is a set, right? That's a question that you could ask me, right? So we're going to talk about sets. So set is basically a collection. Okay, that's very poorly written. That's a collection of objects or things, right? So let's say that you have, I don't know, a basket full of apples. You name it, right? So you could have a few apples, right? And those could be inside of a basket, and that's your set, right? Or you could have your pencil case, and if you open up, right, your pencil case is gonna have probably a pen, a pencil, whatever. You're gonna have a few things, an eraser. That could be your set, things which are in your pencil case. We could have a set of people in a bus. We could have a set people in a classroom, right? Students, class 9 students which attend music. All of those could be sets. Obviously, when we're dealing with maths, most of the time our sets will be things which are more numerical, most of the time. So for example, let's say that I tell you a set with all prime numbers. So, well, all prime numbers, they're infinite, so I would have to stop you somewhere. So let's say that I've got a set with all prime numbers less than 10. So what numbers would be in this set? So let's draw, I don't know, something, and everything which is inside would be in this set. So 2 would be there because it's a prime number less than 10. 3 would be there, 5 would be there, and 7 would be there. Those 4 numbers, they're all less than 10, and they're all prime numbers. So I could write the set P, uppercase P, equals, open squiggly brackets, 2, 3, 5, and 7. Alright, so 2, 3, 5, and 7. When we are writing sets, the names are all uppercase letters. So this is capital P, uppercase P. I could have another set, and well, let's say that I've got a set with all odd numbers less than 10. So odd numbers, 1, 3, 5, 7, and 9. Right? Those are the odd numbers less than 10. I could have B as another set, and I could have all the even numbers less than 10. Since I'm saying less than 10, 10 is equal to 10, it's not less than 10, so 10 would not be in that set. Alright, so I've got here P is the set of 2, 3, 5, and 7, A is the set of 1, 3, 5, 7, and 9, and B is the set of 2, 4, 6, and 8. And also, if you remember, we have chosen those numbers because they are prime numbers less than 10. Here there are the odd numbers, odd numbers less than 10, and here even numbers less than 10. Now, each of those numbers which you have here are called the elements. So, if I asked you, what are the elements of set P, you would have to tell me 2, 3, 5, and 7. Alright? They are the elements of that set. Well, I could ask you how many elements are there in a particular set, and we use this notation n open brackets and we put the set inside. So here, how many elements do I have in set A? So this is my set A. I've got 1, 3, 5, 7, and 9. So how many elements? 1, 2, 3, 4, 5. So the number of elements on set A is 5. How many elements do I have on set P? Remember that you can always pause the video when I ask you any of those questions for you to try and figure out yourself. So n of P, how many elements do I have in set P? It would be 4. So fairly simple, right? So far, fairly simple. Now, if we are asked, is this particular number an element of that set? There is a mathematical way for us to write that. So I could ask you, for example, is 2 an element of set P, right? Is 2 an element of set P, or is 2 a member of set P? Well, yes, it is, right? If you look at set P, 2 is one element of it. Now, is 4 an element of set P? So think about it. Take a look at set P. I've got 2, 3, 5, and 7. 4 is not one of them, so I have to cross this, right? Is an element of. So in this case, 4 is not an element of set P, or 4 is not a member of set P. Okay? So fairly simple so far. We also have our subsets. So as the name implies, a subset is a smaller portion of a set. You have a set and then you have a subset, or a smaller, right, portion. You basically chop it down, you cut it. So if you have, for example, here 2, 3, 5, and 7, if I get, let's say, this other set, this was my set P, right? Now if I get this other set here and call it set D, right? So D would be 2 and 3 only. So is D a subset of P? And well, subset is given as this symbol. So is D a subset of P? So take a look. 2 and 3, which are the elements of D, they are all inside of set P. So yes. Alright, so yeah, that's it. It's true. Here it's also true. Here it's also true. Right? So D is a subset of set P. If it wasn't, so let's see, is C a subset of set A? So if we look at our set A, D is 2 and 3. So I've got 3, but I don't have 2. So it's not. So what do we have to do? Same thing. We cross it. And yeah, that's true now. If it wasn't crossed, then it wouldn't be true. Alright? Now, two sets, they are equal if they are exactly the same. So if I've got, for example, let's say that Mr. Daniel's favorite numbers are expressed by set E. And well, I've chosen 5, 7, 3, and 2. Those were my choices. Is set E and P the same? So take a look at the elements that you have in set E and in set P. So set E and set P, they have exactly the same elements. So they are in fact the same set, just a different order. So E is indeed a subset of P. Okay, so if they are the same, they will be a subset of each other. Now, there is a particular case in which we have a proper subset. So a proper subset is when you have two sets which are not the same, right? One is a smaller portion of the other one, but they have not to be equal. So for example, in this case, E and P, they're not only a subset of each other, but they contain exactly the same elements. There's no element in set P that is not in set E. If I had a set F, and I call this set 5 and 7, then F would be a proper subset of P. So that means that F, all elements of F are on P, but they are not the same. So that's what we call a proper subset. Well, there are a few more notations that we have to know how to deal with. So the first one is the universal set. So the universal set contains everything that we're taking into consideration for a particular problem. So let's say that we're taking into consideration all numbers from 1 to 10. So my universal set would be 1, 2, 3, 4, 5, and there you go. Sometimes you can see some continuation marks here, so you don't have to write all of them, and 10. So it's implied here that you're going from 5 to 6, 7, following the same procedure, the same order, right, the same logic, up to 10. So all numbers up to 10, and including 10 as well. So that could be my universal set. And well, that's it. So you've got all the numbers which you're considering. So if I asked you, okay, P is now all prime numbers in that set, that would be in the universal set. That's exactly what we dealt with before, right? So in this case, nothing would change. However, if I had another situation in which our universal set now continues going, so it doesn't stop at 10, and let's say that it goes all the way to, I don't know, 15. Oops. So what would be now my set of all prime numbers? Now, since I'm specifying that my universal set is up to 15, I don't have to say all prime numbers between 1 and 15 or less than 16. I can just say all prime numbers, because we're limiting the numbers that we're taking into account. So here, all prime numbers. So well, 2, 3, obviously all numbers that we had up to 10, which were prime up to 10, will be here. But now we'll have to check. Well, 10 is not 11. Well, 11 is a prime number. 12 is not. 13 is a prime number. And there we go. That's done. So this would be our new subset. It's a proper subset of our universal set. So if I asked you, okay, is our set P a proper subset of our universal set? And then yes, it is, right? Because they are our prime numbers. They are all inside of this particular set, and that's it for the universal set. Now, what if I asked you, what square numbers do I have? So let's create another set here, set B, and I ask you, what are all the square numbers from 2 to 10? Okay, so from 2 to 10, so that's, yeah, well, we're neglecting one here. So I'm telling you, okay, all sets, we could have another universe, right? 2, 3, 4, and so on, up to 10. Okay, so from the numbers from 2 to 10, what would be our square numbers? So square numbers are any numbers that are other numbers squared. So 2 is not, 3 is not, 4 is 2 squared, so that's a square number. 5 is not, 6 is not, 7, 9 is a square number, that's 3 squared, and that's it, right? So that's a set, right? So what if I asked you, okay, I've got prime numbers from 2 to 10 would be the same. It wouldn't change because 1 is not here, right? So what if I ask 2, is set B a proper subset of set P? Is B a subset of P? So 4 and 9, they are not here, so it's not. Okay, it's not a proper subset, and it's not a subset. So it's neither a proper or a proper subset or subset. It's neither of those. So this is how we would, well, and both would be true. If I tell you, for example, in a question, is this true? And then, well, B is not a subset of P, is it? No, so you would say, well, that's false, that's not true, or you would have to write the symbol like that. Okay. The last thing that we could discuss, or the last couple things that we could discuss, is first the empty set. Okay, so the empty set is, well, empty. So I could have a set D, and, well, there's nothing inside. So this is one way to denote that, or you could just draw your squiggly brackets with nothing inside. There are no elements. So if you would write all the numbers, but since there's nothing, you open it and you close it. That's your empty set. That's your empty set notation. So there's nothing inside. And the last one would be the complement of a set. So the complement is whatever you need to have the universal set. So let's say that we have this first example, the second example here, right? If I asked you, okay, what's the complement of P? So we denote that by a slash, P slash, right, or P prime. So we have to write all the elements which are in our universal set, but are not in our set P. So I've got 1, which is not here. So 1, 2 is in P, 3 is in P, so 4, and we could keep going forward, right? So 6, 8, 9, 10, 12, 14, and 15. So let's check. If we get P with our P prime, we should have all the elements which we have in the universal set. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There you go. That's our complement of a set. It's basically all the elements which you have in U, which are not in your set. So the complement of set P is, what do you have in your universe which is not here? So what is left? What are you missing? That's what a complement means. Alright, so let's take a look at some problems here. Alright, so I've got my universal set, which is all numbers up to 12. I've got my set S, which is 2, 4, 7, 9, and 11. And I've got my set T, which is basically 4 and 11. So let's say that number 1, find n of U, n of S, and n of T. Remember that n here means number of elements. So you can pause the video and find those yourself. I'll just do it, okay? So number of elements in your universal set. I'm going from 1 to 12, so number of elements obviously is 12. Now, number of elements in set S. I've got 5 elements, 1, 2, 3, 4, 5, so 5. And number of elements in set T would be 2. Simple enough. Now, I could ask you also to list sets S prime, so the complement of S, and T prime, which is the complement of T. So which numbers are in our universe but are not in set S? So I've got 1, I've got 3, So just look at your set S. What you're missing, what you're lacking. So 5, 6, 8, 10, and 12. So let's check. If we sum the number of elements, we should get 12, right? So we could also check what's the number of elements on set complement of S and what's the number of elements on complement of set T as well after. So here 1, 2, 3, 4, 5, 6, 7. We have 7 elements and 5 elements. That's 12 elements. Makes sense. Now set T, complement of T, we only have 4 and 11 here. So we're basically going to get all numbers from 1 to 12 except 4 and 11. So it's going to take a while. So 1, 2, 3, 4 is here. So 5, 6, 7, 8, 9, 10, and 12. Alright, so 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10 elements, right? So 10 elements plus 2, 12. So there we go. 2 sets and all the elements are complements as well. So I've got three expressions here, and I would like you to check if those are true or false. So I can give you some time. You can pause the video. However, let's check it out then. So in the first statement here, I'm saying that S is a subset of U. Well, yeah, all elements that I have in set S are in the universal set. So that's true. Okay? True. Now, second one, is S a subset of T? So let's see, is S a subset of T? No, I've got things in S which are not in T. So this is false. Alright? Now, is T a subset, a proper subset of S? So is T a proper subset of S? Well, it is. It's got 2 elements, 4 and 11, and they are both in S. So this is true. Okay? And there you go. Now, just for us to practice, would those be true or false? So 5 is an element or is a member of set S, or 5 is not a member of or is not in set T. So 5, well, if we look at set S, 5, well, it's not in here, so it's not a member, so that would be false. Okay, false. 5 is not an element of T, is not a member of T. That's true, so that would be true. Okay, that's the kind of thing that you're gonna deal with so far.